Hello, I am the magisterial Mr. Daycock, and today I'm going to be teaching you about inflection points and concave and convex parts of curves. So, what do those terms mean, first of all, before we even start on the question? Well, a concave curve is the part of a curve that looks like this. It kind of looks like a cave. You can imagine you could climb into it, and you've got a lot of little people, and they could live in here, and maybe they've got a fire, and they've just discovered fire, and they live in the cave. That is the concave part of the curve. The convex part of the curve is the rest of it, i.e. the bit that's the wrong way up to be a cave. And these are fairly important, because if you imagine this is modelling, say, a hill area, then you could imagine that this is a valley and this is the hilltop, etc. But it refers to rates of change, it refers to the shape of the curve in an important way. So, how do we define that precisely, and what is an inflection point? Well, the inflection point is the change, where it changes from one to the other. So, when it changes from concave on this blue part to convex on the green part. Okay, so let's look at the question. Identify the inflection point of the curve y equals x to the power 4 plus 2x cubed minus 180x squared plus 20x minus 500. And hence, identify where the curve is concave and where the curve is convex. So we can already see a good portion of this. This is the curve right here that we're dealing with, and we've already got a sense of what's going on. We expect it to be concave in the middle, and we expect it to be convex outside. Now, how are we going to use that? How are we going to identify those points? Well, what we're thinking of here, when we're dealing with something concave, is we're talking about the gradient, really. But it's not specifically the gradient, because, as you can see, you can have a negative gradient here, you can have a negative gradient here, you can have negative, positive gradients anywhere on this curve. What matters is how the gradient is changing. And on this concave part, if you can see on this concave part, the gradient starts very positive and becomes very negative. Whereas on the convex part, the gradient starts very negative and becomes very positive. And on this side as well, starts negative, becomes positive. So, and this is basically the definition, on concave, the gradient is going from positive to negative. On convex, the gradient is going from negative to positive. And on the inflection point, there's no instantaneous change in the gradient there. The gradient is instantaneously stable, as it were. So, what that tells us is that we need to consider the gradient function. So we need to, if we have y equals x to the 4 plus 2x cubed minus 180x squared plus 20x minus 500, we need to find out what dy by dx is, which is easy. We get 4x cubed plus 6x squared minus 180 times 2 is 360, x plus 20, and our constant is disappearing. And what do we want to know about this function? So this is the gradient. Well, we want to know how it's changing. We want to know how it's changing. So in fact, we want to think about the change of the gradient. The gradient itself is the measure of change. So the change of the gradient, how the gradient changes with respect to x as we move back and forth in regards to x, the change in the gradient is the second derivative, i.e. we need to do d by dx of dy by dx, which is of course d2y by dx squared. And this is the measure of how the gradient is changing at any given point. So we're going to get 12x squared plus 12x minus 360. And first of all, it's asking us to find the inflection points. And what did I say about the inflection points? Well, the points, they're the stationary points of the gradient, i.e. they're not the stationary points of the curve, they're the stationary points of the gradient, i.e. move that a little bit there. Our inflection points we have d2y by dx squared equal to 0, and this is the key thing. For inflection points, you have d2y by dx squared equal to 0, because it's where the gradient isn't changing. Only instantaneously, but instantaneously it isn't changing. So we get 12x squared plus 12x minus 360 equals 0. I'm going to divide both sides by 12 to make it easier, so I get x squared plus x. 360 divided by 12 is 30 equals 0. And now we've got a nice little quadratic which we can factorise. We get x plus 6, x minus 5 equals 0. And so our inflection points are at x equals negative 6 and x equals 5. And if we look on our graph, that does in fact make sense. If we can see here, the concave was ending at x equals 5, and it was beginning at x equals 6 here. And so that is our concave and convex. Now, we can identify quite quickly where it is concave and convex now. So it is concave for x less than 5 and greater than minus 6, and it is convex when x is less than minus 6 or x is greater than 5. And that answers the question in full, except for arguably how do we justify this? If we didn't have this nice picture over here, how would we justify this claim? Well, we know the inflection points, so we know between the inflection points it can't change. So we know that it is, without the graph, we would still know that between minus 6 and 5, it doesn't change. And equally, outside of those, it has flipped. Well, no, actually not necessarily that. We know there aren't any inflection points. An inflection point does not require a change. So there are sometimes you can get a graph like this, where it's a little bit off there. You're going to get a graph like this, where there's an inflection point here, and it is instantaneously the gradient isn't changing, but ultimately it is convex everywhere. So an inflection point does not prove that it changes from concave to convex. So you need to test each section. But the test is quite simple because we're dealing with the change of the gradient. And for concave, the gradient is getting more negative. So the change is negative. So we get d2y by dx squared less than 0. And for convex, we get d2y by dx squared because our gradient is changing to be more and more positive is greater than 0. Hence, we just need to take our function and test values out. So we know that between minus 6 and 5, it is either concave or convex. So let's plug in 0, try x equals 0. We have 12x squared plus 12x minus 360. Evaluate at x equals 0, and we get negative 360. And therefore, that is concave. Between those values, between minus 6 and 5, it is concave. Now we want to try both places outside, so we want to try less than minus 6. So let's try minus 10. 12 multiplied by negative 10 squared plus 12 multiplied by negative 10 minus 360. That's not 60. Hopefully we want that to be positive, so we're going to get 12 times 100 minus 12 times 10 minus 360, which is 1,200 minus 120 minus 360, and that is indeed greater than 0. And so it's convex for it being less than 0. When we try out a value less than 0, it is convex. And it can't change because there are no inflection points below -6, and therefore there's no way for it to change, stop being convex. And equally, we would try, if we want to try greater than 5, we would try x equals 10. And again, we'd come out positive in a very similar way to this one. And so it would be convex. So lots of different ways of checking where it's convex or concave. You could follow this rule here, and this is a very useful algebraic rule. Equally a very useful rule for the inflection points here. Or you can use the graph and try out values, etc. Okay, let's look at a second example. Because you might not get this nice easy curve like this, you might have to identify the inflection points in the curve y equals x e to the x, and we don't have a graph here. So I'm going to use to identify the inflection points d2y by dx squared equals 0. That's my rule I'm going to use. And let's look at this. So we need to differentiate it once. dy by dx is equal to, well, we need to use the product rule. I'm going to use u equals x, v equals e to the x, and so u dash equals 1 and v dash equals e to the x. And so I'm going to get x e to the x plus 1 e to the x. And this one is those two. This one here is those two. Although that just looks green twice. There you go. Nice and rainbow this time. And that simplifies. We get dy by dx is equal to x e to the x plus e to the x. Now we want to differentiate that. So we get d2y by dx squared. And that's going to give us, well, we actually don't need to differentiate this part again. E to the x obviously differentiates to e to the x. And x e to the x we've just done, we know that differentiates to x e to the x plus e to the x. And then that simplifies to x e to the x plus 2 e to the x. And for inflection points, we need that equal to 0. And to solve this, I'm going to factorize. I get x plus 2 e to the x equals 0, which means either x plus 2 equals 0 or e to the x equals 0. But e to the x cannot equal 0, so that's not possible. And therefore our solution is x equals minus 2. And so we found the inflection point. Now we can try out values larger than minus 2 or smaller than minus 2 and see whether they are positive or negative to find out concave or convex. Equally, the question did ask for inflection points, but as it turns out, there's only one. And if we go up here to the graph, we can absolutely see that at minus 2 there is seemingly an inflection point there. You might not have known it was at minus 2. You might have thought, well, maybe it's at a little bit further along, a little bit further forward, maybe minus 1.5, maybe minus 2.5. But our algebra has told us it's exactly minus 2. And this bit here is convex. And this bit here is concave. And there you have it. That's how you find out the concavity or the convexity and the inflection points of any given curve. Thank you for watching, and I'll see you in the next video.